Hello and welcome. Have you ever wondered how you can possibly know the exact speed of a car at one single instant, or find the precise slope of a curving hill at just one tiny point? I mean, it sounds kind of impossible, doesn't it? Well, today we're pulling back the curtain on the secret, a massively powerful idea in math called the limit. It's the single concept that makes all of calculus tick. Let's dive right in.
All right, so here's our game plan. First, we're going to look at what happens when graphs get weird and, well, break. Then we'll introduce the brilliant solution that is the limit. After that, we'll see how limits let us talk about those breaks with perfect precision. And then we're going to push the idea to its extremes, literally. And finally, we'll tie it all together for the big aha moment, why this one idea is the bedrock of all of calculus.
So to really get why we even need limits, we first have to wrap our heads around the problem they were invented to solve. You know, in a perfect world, every graph would be this beautiful, smooth, continuous curve. But let's be real, the world's a messy place, and so are a lot of mathematical functions. We need a way, a language, to describe exactly what's happening at those points where things aren't so perfect.
So what does it even mean for a function to break? You know, when you're drawing a graph and you suddenly have to lift your pencil off the paper, how do we talk about that moment with the precision of mathematics? For starters, a function might look like a perfectly smooth road, but then have one single tiny point just missing. Think of it like a manhole cover that's just gone. The path leading up to it is totally clear. The path leaving it is clear, but that one specific spot? Poof, it's vanished. We call that a hole.
Or you could be cruising along a function. Everything's going fine, and then, bam! It suddenly jumps to a completely different level. It's like a broken escalator, there's just no connection between the two pieces. This sudden split is called a jump.
And then, you've got the most dramatic break of them all. As you get closer and closer to a certain point on the graph, the function just goes wild. It either skyrockets straight up to positive infinity or plummets down to negative infinity. It creates this kind of invisible wall that it gets infinitely close to, but, and this is key, it will never, ever actually touch it.
So we have a hole, a jump, and an infinite spike. Three totally different looking problems, right? Well, what if I told you that mathematics has one single, unbelievably elegant tool that can describe every single one of them with perfect precision? That tool, my friends, is the limit.
So, what on earth is a limit? The best way to think about it is with an analogy. Imagine you're walking along a path and there's a little pothole up ahead. Now, the limit doesn't care about what's in the pothole. It's not asking what happens when you get to that exact spot. Instead, the limit asks, hey, based on the direction of the path just before the hole, where would you have stepped if the hole wasn't there? It's all about the trend, the intention of the path. And this is the most important thing to remember. A limit is all about where you're headed, not where you actually land.
And this idea of approaching gets even cooler. We can actually look at the value a function is heading towards from just one side at a time. We can sneak up on that point from the left, or we can sneak up on it from the right. We call these one-sided limits. But, and this is a huge but, for a true overall two-sided limit to exist at that spot, both sides have to be on the same page. The path coming from the left and the path coming from the right must be heading towards the exact same value. They have to agree.
Okay, tool belt on, we've got our new concept, the limit. Now let's go back to those three broken graphs we started with. It's time to put this tool into action and see how it gives us a super precise way to talk about what's really going on.
Let's start with that hole in the road. Using our new lingo, what's happening? Well, as we approach from the left and as we approach from the right, the function is heading to the exact same value. So the two-sided limit totally exists. The only problem is that the actual function's value right at that point is either missing or maybe it's defined somewhere else entirely. The limit is basically screaming at us, hey, the path should go right here.
And the jump? This is the textbook case of one-sided limits getting into a fight. As you come in from the left, the path is heading toward one specific height, but as you come in from the right, it's aiming for a completely different height. Because the left-hand and right-hand limits aren't equal, the overall two-sided limit doesn't exist. That disagreement is the jump.
Okay, so far we've been using limits like a microscope, right? Zooming way in on these tiny little problem spots. But get this, we can also use them like a telescope. We can zoom out and ask, what does this graph do at its absolute farthest edges, way out towards infinity?
Remember that function that just shot off to infinity?
Well, the formal definition for that invisible vertical wall, the vertical asymptote, is all about limits. It's actually pretty simple. If, as you get closer and closer to a certain x value, the function's limit is positive or negative infinity, then congratulations, you found a vertical asymptote. The limit blowing up is the mathematical definition of that invisible wall.
Now let's flip that question around. Instead of asking what happens as we approach one specific point, what if we let the input, x, go on forever towards positive or negative infinity? If the function starts to level off and get closer and closer to a specific finite height, that value is the horizontal asymptote. The limit at infinity tells us the graph's ultimate long-term behavior.
And these powerful ideas aren't just for some simple made-up graphs. They apply to all sorts of functions, even the famous ones. Take e to the x, the function that models exponential growth. As x goes way out to the left, toward negative infinity, the function flattens out and gets incredibly close to 0. That's a horizontal asymptote. Or look at its inverse, the natural log. As x gets ridiculously close to 0 from the right side, the function just plummets down to negative infinity. That's a classic vertical asymptote. The point is, no matter how complex the function, limits give us a universal language to describe its behavior at these critical spots.
So, we've defined holes, we've defined jumps, we've defined asymptotes. We've even looked at what happens at the ends of the universe for a graph. But you might be thinking, okay, that's neat, but why is this so important? Well, get ready. This next part is the real aha moment, where we connect all these dots to the true power of calculus. This table really puts it all together beautifully. Look at this. Every single one of those visual problems we started with on the left now has a precise rock-solid definition on the right, and it's all based on the idea of limits. A hole? That's just when the limit exists, but the actual point doesn't match up. A jump? That's when the left and right limits disagree. An asymptote? That's just a limit that's heading towards infinity. It's this beautifully complete system for describing exactly how functions behave.
But here it is, the ultimate punchline, the central tool of all of calculus, the derivative. The very thing that lets us find the speed of a car in a single instant or the slope of a curve at one specific point is, at its heart, a limit. Think about that paradox. How can you measure change if no time has passed? The answer is, you can't, not without a limit. The derivative is literally defined as the limit of an average rate of change as that time interval shrinks down to nothing. This is why understanding limits isn't just helpful, it is the absolute, non-negotiable bedrock of calculus. The whole building stands on this one idea.
Ultimately, limits are our mathematical microscope for the infinitely small. They allow us to tame the concept of infinity and to talk rigorously about a single instant in time. And that just leaves us with one final big question. If this one idea is powerful enough to solve the paradox of instantaneous change, what other seemingly impossible problems out there in our world can it help us understand and maybe even solve?